So let's look at another example of a situation where we have a function and we would like to know how its graph behaves far away from the y-axis. So in other words, if it has any horizontal asymptotes, we want to find them, and that's what we're asked to do here in this example. So here's our function, and we're going to start out in the same way as last time. We're going to start off by taking the limit as x goes to infinity of f of x. That's how you start these. That'll always be your first step when you're looking for horizontal asymptotes of a function. Okay, well, our function, limit as x goes to infinity of the square root of 2x squared minus 1 all over x. That's the function we actually have, right? And I'm actually going to start working downwards in my steps because I want to leave a bit of room over here to write some comments. So what are we going to do here exactly? Remember what we did last time? We factored out the highest powers of x from the numerator and the denominator, respectively. Well, that was a bit of a different situation because that was a rational function in our previous example. Let me just dig it out here. In our previous example, our function was rational, right? We had a polynomial on the numerator and a polynomial on the denominator. So we factored out the highest power of x from each of them, and then we canceled them out. It's not going to work out quite the same way in this example because this is not a rational function, right? We have a square root in our numerator, but we're still going to kind of use the same principles. But what we have to do is we have to work within this square root, at least at first. So let's start out by saying, okay, well, that 2x squared minus 1, let's just factor out an x squared. But we have to understand that that's all taking place inside the square root. Let me show you what I mean. So we're going to see the limit as x goes to infinity. So the square root is going to turn into this. You're going to have x squared times 2 minus 1 over x squared. And all of that is still inside the square root. So you can see what we've done is we did a factoring inside the square root, but the square root stayed where it was. So we still haven't changed anything. And now we're going to use properties of radicals, which say that we can actually split this up. We can split this up as the limit as x goes to infinity. And our numerator is going to become the square root of x squared times the square root of 2 minus 1 over x squared. And the denominator will still be x. We haven't done anything to the denominator. So now what's going to happen here with this square root of x squared? This is where your attention should be next. Is this just going to cancel? Like, do the square and the square root cancel? Well, not quite. What you have to be careful. If you take the nth root in general, if I take the nth root of x to the n, so for some positive counting number n, let me call this a note because this is important. So if I take x and I raise it to the power of some positive integer n, so some positive counting number like 2, 3, 4, 5, 6, 7, whatever the case may be, anything at all, and then I take the exact same root afterwards, the question might be, well, do the root and the power cancel out and just give you back x? And the answer is sometimes. Roughly half the time you'll get x back, and the other half of the time you'll get the absolute value of x back. So here's the full story. It's just x if n is odd. But if n is even, then it's going to be the absolute value of x. Okay, so actually in our case, this is like the rule here in the case where n is equal to 2. Because of course if you have a square root, like a 2 here, you actually don't write it. So there's a hidden invisible 2 here, right? So this is actually going to be the absolute value of x. So you have to be careful with that. Absolute values, whenever you're dealing with a limit, you have to handle them carefully. Okay, so we're going to have the absolute value of x times the same square root we had before, all divided by x. Okay, well then what about this absolute value of x? Remember before we've seen examples of limits where you can't just cancel the absolute value of x with an x, because they're not quite the same thing, right? So what you have to do is we have to look carefully at this absolute value and we have to deal with it somehow. We have to find another way to write it that doesn't involve absolute value. And then let me just remind you how absolute values work analytically. If I have the absolute value of a real number x, it's just the same as the number x in the case where x is greater than or equal to 0. But if x is less than 0, then it's negative x. Right? So actually in this case, remember we're taking the limit as x goes to infinity, so the values of x that we're concerned about in this calculation are all positive, because we're talking about what happens when x explodes in the positive direction. So this can be just replaced with x. because this is the rule that's satisfied for this limit. So what we're going to have now is the limit as x goes to infinity. We'll have x times the square root of 2 minus 1 over x squared all over x. And then now, finally, if you've been wanting to cancel those x's, now is your chance. Now you finally can, because they're a common factor of the numerator and denominator. They cancel out nicely, and you just get, should I go sideways or down? Based on how much more we have to do, I think we can manage to go down here. So we'll get the limit as x approaches infinity of just the square root of 2 minus 1 over x squared. And then now, actually, we're in a position to identify exactly what the answer is, what this limit's going to evaluate to. We're actually in a position to take the limit, because this 2, nothing's going to happen to this 2, right? But the 1 over x squared, we know exactly what's happening to the 1 over x squared, right? As x gets very, very large, this fraction just gets smaller and smaller. So what's happening here? This is approaching 0. So the limit, then, we can evaluate it. And I'm going to slide up. We still have some more work to do, so I'm going to put my last step over here. So if this term disappears, it's really just the limit's going to turn into the square root of 2. So that tells you that y equals the square root of 2 is a horizontal asymptote of this function, because we took the limit as x goes to infinity of f of x, and we got the square root of 2. Okay, so but remember, we have to check the other direction as well, right? Because there might be another horizontal asymptote in the negative direction. So let's take the limit now as x goes to negative infinity. This is another calculation that we have to perform now. So what we're going to get is the limit as x goes to negative infinity. We have what? Square root of 2x squared minus 1 all over x. So we're starting out in the exact same way that we did before. Now it's worth paying attention here and looking at what some of our work we can just recycle, right? I mean, you could just copy the exact same process and go through it carefully step by step, and there's nothing wrong with that. In fact, it's probably good practice. But let's take a look at the work we did up here and see if we can recycle any of these steps. Notice that from this step to this step to this step to this step, all the way to this step, never did we ever look down here. We didn't look where x was actually going. So taking f of x and replacing it with its definition, doing some factoring, splitting up the square root, replacing the square root of x squared with its absolute value, with the absolute value of x. All of that was strictly algebraic, and this holds for all values x. So why don't we just jump right to this step, because it wasn't until the next step that we actually took advantage of the fact that x was going to positive infinity. So for our next step, I'm going to say let's write this as equal to the limit as x goes to negative infinity of the absolute value of x times the square root of 2 minus 1 over x squared, all divided by x. So now it's going to be a little bit different than last time. But we're still going to use this definition of absolute value. But this time, as far as our limit's concerned, the values of x are going to be negative, because x is exploding in the negative direction here, right? So actually, in the definition of absolute value, when we work out what this is, the value of x is actually going to be negative. So we're going to replace the absolute value of x with negative x. So our next step is actually going to be the limit as x goes to negative infinity of negative x times the square root of 2 minus 1 over x squared, all divided by x. So we do have this lingering negative sign now, but that's okay. So what? At least we got rid of the absolute value. We can still cancel these x's now. We still have a common factor of x in the numerator and denominator, so cancel those. And then what are you going to get? We're going to have the limit as x approaches negative infinity of negative the square root of 2 minus 1 over x squared. And now we can just do the same analysis we did up here, or perform the same observation. 1 over x squared, as x gets arbitrarily large in either direction, right? We've talked about this before. If x blows up in the positive or negative direction, expressions like this are going to go to 0. They're going to become insignificant. So this is going to 0. So if we actually take the limit, this term will disappear, and we'll just have negative the square root of 2, which I'll write here. Okay, so one of our limits to infinity gave us positive root 2 and the other one gave us negative root 2. So we can conclude now, let's put the conclusion here. Therefore, y equals the square root of 2 and y equals negative the square root of 2. Both of those horizontal lines are horizontal asymptotes. So our horizontal asymptotes of our function f. But how about I just say they're horizontal asymptotes, because there's only one function that we're looking at. They're horizontal asymptotes to the graph of this function. So it's pretty obvious what we mean if we stop there. So let's just say it like that. So that is an example of a case where if you aren't careful and you forget to, I can just get them on the same screen at once. If you aren't careful and you forget to calculate one of these, you'll miss one of your horizontal asymptotes and you'll only get half the story. So make sure to check in both directions if you're asked to find all the if you're asked to find all the horizontal asymptotes of a function.